The topic of the session is trigonometry. What is trigonometry in mathematics? What is trigonometry? Trigonometry has been derived from three different words: trigonometry. The trigonometry has trigonometry. Now, tri is 3, which is a three-sided figure, which is a triangle. We know that a three-sided figure is a triangle, and gono is angle, and metry is measure. So with these three basic words split out of trigonometry have their own individual meanings. Tri is 3, gono is angle, and metry is measure. Measure of three angles of a triangle is called trigonometry. So trigonometry split as trigonometry is measure of three sides or measure of three angles of a triangle is called trigonometry. In general, what is the purpose of trigonometry? Why did mathematicians effort in researching on identifying the topic of trigonometry? What was the need for mathematics or the branch of mathematics to come out with the purpose or the reason for identifying this topic and its significance in daily life is the biggest question out here. The purpose or the need for trigonometry. Imagine, let's come out with a small activity to understand why trigonometry is very important in daily life. Say, for example, imagine I go into the deep forest and then I just come into a place where I have a small lake bed where all water is flowing in the lake bed. So here is the lake bed, and here is all the forest complete, and even the other side there is the forest out there. So I was going on a trekking on my trip, and then I just came till here and I was halting to know how I can cross to the other side of the small lake bed or the river flowing canal to go to the other side of the forest. So I was puzzled on imagining that I can do that if I put some wooden log out here, and then this wooden log on which I'm going to crawl or walk carefully to go to the other side. To do this mathematically, I paused for a while to imagine how much of the wood or the log of wood I can put on this canal bed to go to the other side. I wanted to estimate the length of the wood log I need to put on the river flowing small canal. So this puzzled me because I couldn't exactly measure the length of the width of the canal or the width of the river flowing there by just measuring with a tape, because I cannot do that manually because for a while I don't have the log here. So how do I find the length, the width of this using the mathematics or the branch of mathematics is the biggest question when I go and stand at the bank of the river this side. So these kind of questions were big puzzles in identifying how we can successfully go to the other side of the forest. This can be done, and this is strictly possible if we know the topic of trigonometry. Trigonometry helps us in estimating this distance without actually measuring it. The power of trigonometry is to measure these distances without actually measuring with tape. Imagine I have a long tower, say it is a Qutub Minar. I have a Qutub Minar here. And then I stand here. I just stand here. And then I want to find the height of the Qutub Minar by just standing out here, which is just 5 meters away from here or 15 meters away from here. Then how do I find the height of the Qutub Minar without actually measuring with tape? It is possible using the topic of trigonometry. Trigonometry is how we introduce the concept of trigonometry, which solves many problems like finding the height of the Qutub Minar or crossing the length of the river onto the other side, by crossing to the other side of the forest by just estimating the width of the river. So all these real life puzzles or tasks can be overcome if we know the concept of trigonometry applied in real life. Let's consider a right triangle and see how the real life puzzles can be solved using trigonometry connected with right triangle. So let's see how a right triangle is connected with the trigonometry. To come with this real life example, if this is the Qutb Minar, the height of which we need to find, imagine we can convert this real life puzzle into a right angle triangle or a right triangle. If the person standing here is watching the top of the minar, then this being perpendicular clearly makes me understand that this real life problem can be converted into a right angled triangle. This being the height of the Qutb Minar, and this being the distance from the person to this, and this being the distance from the eye to the top of the minar, as can be taken. Therefore, if I take a right angled triangle with vertices A, B and C, then there are three important factors we must know in right angled triangle. If this angle is 90, then in this case of the right angled triangle, if angle A is 90 degrees, then BC is called the hypotenuse because this is opposite to 90 degrees. The side opposite to 90 degrees will always be the longest side in a right angled triangle, and that side is called the hypotenuse, the longest side. So BC is called hypotenuse next. If I take this angle as theta, then that means the angle which the person is making with the top of the minar is theta, then the angle which the person makes will be considered as angle ACB or angle C, which is theta. So using this, we understand that any side opposite to this angle is called opposite side. This, of course, is hypotenuse, and this is called adjacent side. So these are the three sides which are very important out here, because this is called opposite side, this is called hypotenuse, and this is called adjacent side. Opposite because this side is opposite to angle theta, hypotenuse because this is opposite to 90 degrees, and finally the third side, which is this, is called adjacent side. This is just adjacent to the angle. So BC is hypotenuse, AB is opposite side, and AC is adjacent side. Is how we get each of the sides, hypotenuse, opposite and adjacent, this being the angle. Therefore, if suppose I have a triangle with angle out here, then in this case, this being 90, I understand that this is hypotenuse, usually hypotenuse denoted with H, and opposite side denoted by O, and adjacent side denoted by A will have its opposite side here and adjacent here. The opposite side comes here because the angle theta is here, and opposite to that will be O. Is how we get. Suppose I have a triangle, say, so this is 90 and this is theta, then clearly angle 90 degrees opposite to that will be hypotenuse, opposite to theta is O, and this is adjacent. Is how we understand the different right angle triangles taken in different forms, finally giving us the opposite side, adjacent side and hypotenuse for a right angled triangle. Trigonometric ratios is one of the most important factor of trigonometry. The origin of trigonometry has finally led to trigonometric ratios, which help us in solving the previously discussed puzzles. The main intention of trigonometric ratios is to solve some of the mysteries, like finding the height of the Qutb Minar or crossing the river or finding the width of the river flowing opposite to go to the opposite side of the forest. So how do we see? Let's see how trigonometric ratios have come into existence. What is the purpose for inventing the trigonometric ratios, or we can call this as origin of trigonometric ratios. So let's see how it comes into existence, of course connected with right angled triangles. So in this case, let me imagine a right angled triangle which is, say, quite very small out here. I take a very small right angled triangle, in this case right angled at this, and this being theta. So if this is theta and this is right angled triangle, then obviously we know that the side opposite to right angle is hypotenuse and the side opposite to theta is opposite, and obviously the third side is adjacent, is what we understand in this triangle 1. So this is triangle 1. Similarly, I take the triangle 2. So in this case, let me take a little bigger triangle, say. In this case, same angle theta. I do not change the angle theta, which is for this. The same angle is maintained out here. And then this is opposite, this is hypotenuse, and this is adjacent. Next, I consider the third triangle, the triangle 3, which is quite big. This is the triangle which is bigger than this and more bigger than this, and here I take the angle theta. Now let's identify H, O and A. This is H, this is O, and this is A. Now since each of them are with different dimensions, I take this O1, H1, A1, O2, H2, A2, and O3, H3, A3, because the three sides are different. Each of the respective three sides, H, O and A, are different. So for triangle 1, my hypotenuse is denoted with H1, opposite with O1, and adjacent side with A1. But interestingly, for each of them, the angle is same. This is a very important note to be made, that here one of the angle theta is same, but each of the sides are with different dimensions. Smaller triangle, medium triangle, and a bigger triangle. So here theta is same, it is not changed. So let's see what interesting factors come into existence in the trigonometric ratios. So mathematicians started identifying for triangle 1, say I take for triangle 1, I just divide opposite side with hypotenuse, and then for triangle 2, I just divide the opposite side with H2, and for triangle 3, I divide opposite side with hypotenuse. Interestingly, mathematicians have come out that for triangle 1, where the theta is same, O1 by H1 gave an approximate k value. Say it is some k. When divided, it gave some decimal value which was denoted with some k. Similarly, for triangle 2, with the same angle theta, when this was divided with this, the measurement of O2 divided with H2 has given the similar approximate value of k. It gave the same k as obtained in triangle 1. Further, when this side was divided with this side approximately with the same angle theta, this dimension by this dimension of the third triangle also gave an approximate value of k. That means each of the triangles had k which was approximately same, but not exactly equal, but with minute error in the value of k. Therefore, this made mathematicians understand on the common factor between each of the triangles where one of the angle is same. In a right angle triangle where theta is same, then there was some relation between opposite side and hypotenuse of each of the triangles where all of them were k, etc. So the mathematicians started calling that opposite by hypotenuse as sine theta. The purpose of inventing this common thing was denoted with opposite side by hypotenuse, and it was defined as sine theta. The word sine, which stands for sine of theta, was taken as the root. So sine theta was the value given for opposite side divided by hypotenuse. So whatever k I get here is now called sine theta. When I divide the opposite side by hypotenuse, the value I obtain is called sine theta. And that is for any triangle with angle theta. I take a big size of a triangle as huge as the sky and take the angle theta to be same, then opposite side by hypotenuse of that triangle will be same as opposite side by hypotenuse of this smaller triangle. That's how we conclude through the opposite by hypotenuse. Similarly, as we connected opposite and hypotenuse, there were also similar comparisons made from adjacent by hypotenuse. So let's see what interesting facts have come through adjacent and hypotenuse connected through the ratio. Next comes connecting adjacent and hypotenuse. So for triangle 1, triangle 2 and triangle 3, I have adjacent by hypotenuse is approximately equal to adjacent by hypotenuse approximately equal to adjacent by hypotenuse, which was denoted with some k. This was also true for adjacent divided with hypotenuse, just like opposite with hypotenuse. So whatever adjacent length divided by hypotenuse, and this by this and this by this of any size triangle, provided theta is same, has given me all equal values, and that equal value was denoted with cosine theta. Cosine theta is what it is denoted with. So this value has been denoted with cosine theta, or cos theta is called adjacent by hypotenuse, is what has been derived as the formula for trigonometric ratio. One of the trigonometric ratios is cosine theta or cos theta is adjacent by hypotenuse. Now lastly, let's see the comparison between opposite side and adjacent. We have compared between OH, HA. Now comes the turn on comparing between A and O. So let's see what is the interesting conclusion made out there by the mathematicians. Now let's see the relation between opposite and adjacent side, where for triangle 1, triangle 2 and triangle 3, I have opposite by adjacent for triangle 1 is also equally, approximately equal to the opposite by adjacent of the triangle 2. Similarly, if we take the opposite side with adjacent side for triangle 1 is approximately equal to O2 by A2, approximately equal to O3 by A3, which is some constant K. This also made the mathematicians come out with tangent theta or tan theta equals O by A. Is how we understand the trigonometric ratios. So these are the three trigonometric ratios. Now that we have connected A with H, H with O, and O with A, we have three trigonometric ratios invented by mathematicians for a right angle triangle using this purpose of same angle theta. So therefore, let's recap with how the trigonometric ratios are framed into formulae. Therefore, for three trigonometric ratios which we have identified for a right angle triangle are, for this right angle triangle, if this is theta, then this is opposite side and the hypotenuse and the adjacent side. Then the first trigonometric ratio, we call it as sine theta, is opposite by hypotenuse And the second trigonometric ratio, which is called cos theta or cosine theta, is adjacent by hypotenuse, and the third, which is tan theta or tangent theta, is opposite by adjacent, are the three trigonometric ratios identified for a right angled triangle. Is how we understand sine, cos, and tan, the three trigonometric ratios in order. Now let's see the reverse trigonometric ratios or reciprocal trigonometric ratios. It's very simple that we have already discussed for a right angled triangle where this is theta and this is right angle, this is hypotenuse, opposite and adjacent. We had three trigonometric ratios, sine theta, cos theta, and tangent theta, as opposite by hypotenuse, adjacent by hypotenuse, opposite by adjacent. Now, these three trigonometric ratios, which are called the standard trigonometric ratios, have led to the reverse trigonometric ratios, which are cosecant theta, or we can call this even as cosec theta, equals 1 by sine theta. So reciprocal of sine is called cosecant theta, and the reciprocal of this would definitely make this reverse O by h to h by O. Therefore, hypotenuse by opposite is referred as cosecant theta, and opposite by hypotenuse is referred as sine theta. To start with this. Then secondly, my cos theta when reversed gives me secant theta or sec theta. The short form of secant theta is sec theta, and this is nothing but reciprocal of cos, which we refer. Reciprocal of cos is secant, and then that is h by a, because a by h is cos. I get this as hypotenuse by adjacent. Similarly, when I take the tan, the reciprocal of tangent theta is called cotangent theta. Therefore, this is called cotangent theta, written in the short form as cot theta, so that this reduces to the reciprocal of tan. So the reciprocal trigonometric ratios have their own formulae, where cosecant is 1 by sine, secant is 1 by cos, and cot or cotangent is 1 by tan. Therefore, tan theta being O by A will be A by O, that is adjacent by opposite, is what we get for the reciprocal trigonometric ratios taken as a formula. Reverse trigonometric ratios are cosecant, secant, and cot. And the standard trigonometric ratios are sine, cos, and tan, have their own respective formulae with their own definitions. Now let's see some practice problems on connecting the trigonometric ratios with the right angled triangle. That is, I give a right angled triangle, and using the right angled triangle, we need to find the trigonometric ratios. Let's see how we can do that. Before doing the problem, let's identify that there are 6 trigonometric ratios which we have discussed in the session. Sine theta, cos theta, tan theta, cosecant theta, secant theta, cot theta are the 6 trigonometric ratios which we are going to find using the given problem. Now here, tan A is 3 over 4, then have to find all other trigonometric ratios, that is sine, cos, cosecant, secant, and cot, because tan is already given. So with the trigonometric ratio, I try to use the right angled triangle to find the other trigonometric ratios with the respective formulae as discussed in the previous session. So let's draw a right angle triangle connecting the trigonometric ratios. So this is a right angle triangle. Say the angle is A out here, because the angle is not theta, it's A. I take the angle A out here. Therefore, I take the trigonometric ratio with angle A, where one of my trigonometric ratio is given as tan A equals 3/4. But since the trigonometric ratio 3/4 is opposite by adjacent using the formula, therefore my opposite is 3 and my adjacent is 4. But because this is in fraction, I don't know what is the common multiple divided for both numerator and denominator. Therefore, opposite by adjacent equal to 3/4 implies my opposite side is 3k and my adjacent side is 4k for k belonging to z. Of course, z plus for k belonging to z. It can be negative. So for any integer k, the opposite side is 3 times of the multiple constant k, and adjacent is 4 times of k, is what we get. It can be even r. K belongs to z, or all the real numbers which come into existence except 0. All non-zero real numbers is what we consider here. Therefore, for k belonging to all real numbers except 0, I have opposite side is 3k and my adjacent side is 4k, so that my opposite side is 3k and adjacent side is 4k is what I get. Now from this, how do I find the hypotenuse? How do I get the hypotenuse is the biggest question. Now here we use the Pythagoras theorem to find h. That is, by Pythagoras theorem, hypotenuse square is opposite square plus adjacent square. But why is the need to find the hypotenuse? Because the question is to find all other trigonometric ratios. To start with sine theta, which is opposite by hypotenuse, I need the hypotenuse in the denominator of sine theta in order to find the trigonometric ratio sine. Therefore, we need each of opposite, adjacent, and hypotenuse to find all other trigonometric ratios. Therefore, by using Pythagoras theorem, we extract h. That implies this gives me hypotenuse square is opposite square, which is 3k whole square, plus adjacent square, which is 4k whole square, which on further simplification gives 9k square plus 16k square, that is 25k square, is h square. That implies my h is plus or minus root 25k square, that is plus or minus 5k, but I don't take, assuming k is positive, for k greater than 0, I assume hypotenuse cannot be negative, so I take 5k. Because I don't take the negative value, because lengths are always positive. Therefore, hypotenuse is 5k, and coming to the opposite, we already know that the opposite is 3k and adjacent is 4k. So this is 3k and adjacent is 4k. Now these three values we utilize in finding the all other trigonometric ratios. Let's see how we can find each of the trigonometric ratio using h, o, and a. Therefore, we have the opposite side, which is 3k, and adjacent side, which is 4k, and hypotenuse, which is 5k, found recently using the Pythagoras theorem. Now using this, I have to find each of the trigonometric ratios. To start with sine A, which is opposite by hypotenuse, is what we have as the formula for sine theta. Now what is the opposite side? Clearly I have this as 3k, so I substitute this as 3k by hypotenuse, which is 5k. And this can be cancelled because k is not equal to 0. Therefore, since k is not equal to 0, I can cancel this and I get sine A as 3 over 5. So this is one of the trigonometric ratio which is obtained using the formula for sine theta. Let's find for cos. Cos A is given by adjacent by hypotenuse, where my adjacent is 4k and my hypotenuse is 5k. Cancelling this, I get 4 over 5 because k is not equal to 0. So we get cos A as 4 over 5. Similarly, tan A is already known. So once I know sine, cos and tan, I can easily find cosecant, secant and cot. So let's see how we can find cosecant, secant and cot using sine, cos and tan. So the session is about the trigonometric ratios of complementary angles. So what are complementary angles? The sum of the angles is 90 degrees, then we say the two angles are complementary. If the sum of the angles is 180 degrees, we say the two angles are supplementary angles. Is the session for today. Now that we have already discussed about supplementary and complementary angles, so let me just give a brief introduction. If angle X plus angle Y is 90 degrees, then we say this X and Y are said to be the complementary angles. Now, using with the definition of this complementary angles, let's see how the trigonometric ratios of complementary angles are considered and what outcome comes out of the discussion of trigonometric ratios of complementary angles. To start with the right angle triangle. Let me consider a right angle triangle. So this is A, B and C. And let me say the length opposite to angle A is A, and this is B, and this is C opposite to this. So A, B, C are the lengths of the sides of the triangle, right angle triangle A, B, C. Let me take this to be theta, angle theta. Then if this is theta and this is 90 degrees, we know that sum of all the three angles of a triangle is 180 degrees. Therefore, this being 90 and this being theta, obviously this would be 90 minus theta is what we get for the third angle. Now this is what makes the definition of complementary angles, because when I sum up angle B plus angle C, I get complementary angles. That is, in the triangle ABC, I clearly see that when I sum up angle B plus angle C, I get 90 degrees, and hence this property is nothing but the complementary angle property. And using this complementary angle property of a right angle triangle with angle B plus angle C equal to 90 degrees, we are going to connect the trigonometric ratios with the property of complementary angles. So let's see how it is possible. So I take two sets of trigonometric ratios for each of the angle theta and angle 90 minus theta. Therefore, if I take theta for angle theta, then we have sine theta equals opposite by hypotenuse, cos theta is adjacent by hypotenuse, and tan theta is opposite by adjacent of the respective angle theta. So let's initially find for theta all the three possible trigonometric ratios. So in this case, let me start with sine theta, which I clearly understand that from this triangle sine theta is opposite by hypotenuse. Therefore, my opposite side being B, this would be B by hypotenuse, which is A, comes out to be B by A. So my first trigonometric ratio for the angle theta is sine theta equals B over A. Similarly, let's start with the next trigonometric ratio, cos or cosine theta. So here the cos theta is adjacent by hypotenuse, which is nothing but for the angle theta, adjacent is C and hypotenuse is A. So I get this as C over A. Thirdly, to start with tan theta. Tan theta is opposite by adjacent. Therefore, my opposite to angle theta is B and adjacent is C. So I get this as B over C is what I get for this angle theta, that is angle B. Next, let me take the angle C, which is 90 minus theta, as obtained from sum of all three angles of a triangle. So using this angle, let's see what are the trigonometric ratios defined for that particular angle 90 minus theta. So here for 90 minus theta equals angle C, and here this equals angle B. Let's see what are the possible trigonometric ratios. Sine of the angle here is 90 minus theta, so in place of theta I get 90 minus theta after the sine. So I need to find sine of the angle 90 minus theta, that is angle C. In this case it is opposite by hypotenuse, but here the opposite side is not the same as this, because opposite to 90 minus theta is C and hypotenuse is A. For opposite of theta is B and opposite of 90 minus theta is C. So opposite side changes with the angle. This angle has its opposite side here. This angle has its opposite side here. Therefore, for 90 minus theta, my opposite side is C. Therefore, I get C over hypotenuse, which is A. Similarly, I have cos 90 minus theta, which is adjacent by hypotenuse. So adjacent to the angle 90 minus theta is B, and hypotenuse is of course not going to change. It is fixed, which is A. So this would be B over A. And finally, my tan 90 minus theta is opposite by adjacent. Therefore, my opposite being C and adjacent being B is C over B, is what I get for two particular angles, theta and 90 minus theta. Now, as I compare these two trigonometric ratios for the angle theta and 90 minus theta, which are the complementary angles, we come with an interesting outcome that if sine theta is B over A, is nothing but same as cos 90 minus theta, which is also B over A. This matches with this. That means this is equal to this. Similarly, C by A matches this, which makes me understand that cos theta is sine 90 minus theta, because their right hand sides are same, being C over A. This being C over A and this being C over A. Thirdly, I have tan theta is B over C, tan 90 minus theta is C over B, which makes me understand that this is reverse of this. That is, each of them are reverses of each other. So that makes us understand that one gets converted into cot, tan to cot or cot to tan. So initially, to start with, let's identify the first two trigonometric ratios with their comparison. So here I identify that sine theta is clearly cos 90 minus theta. That is, we have a formula, this equals this and this equals this. So let's start with sine. So I have sine 90 minus theta is C over A, which is equal to cos theta. So this is the formula which is extracted from the trigonometric ratios of a right angle triangle. And similarly, my cos 90 minus theta is sine theta, is what I get from the ratios. Further, tan 90 minus theta is C over B, which is nothing but 1 by B over C, because C over B I can write as 1 over B over C, so that this reduces to 1 by B over C, which is clearly tan theta, and therefore this one substituted here gives me 1 by tan theta is cot theta. Therefore, I have three derived formulae. Sin 90 minus theta is cos theta, cos 90 minus theta is sin theta, and tan 90 minus theta is cot theta are the three basic formulae which are identified for the trigonometric ratios connected with complementary angles, deriving three basic formulae. Sine 90 minus theta equals cos theta, cos 90 minus theta equals sine theta, tan 90 minus theta equals cot theta is what we conclude. Now let's find the other three trigonometric ratios connected with complementary angles, that is cosecant, secant and cot. Now initially, to start with, the three basic formulae which we have identified are first with sine 90 minus theta, next with cos 90 minus theta, and next tan 90 minus theta are the three formulae which we have obtained for this being cos, and this being sine, and this being cot. Now these three will help us in obtaining the reverse trigonometric ratios. For this reduces to 1 by sine is equal to 1 by cos. I have taken the reciprocal of both of them because when x is equal to y, 1 by x equal to y. Since x equal to y implies 1 by x equals 1 by y. So using this property, I get this, which on further simplification gives cosecant 90 minus theta is 1 by cos, which is secant theta, is the formula which we obtain for the first connected with this. Similarly, this gives me secant 90 minus theta equals cosecant theta is what is derived for the second reverse trigonometric ratio. And finally, to start with this, tan reversed gives me cot on the right, cot reversed gives me tan is what I get as the three other trigonometric ratios, cosecant, secant and cot is what we get on the whole. So the trigonometric ratios of complementary angles connected with six basic formulae, sine, cos, tan, cosecant, secant and cot, differing by 90 degrees. So let's see the applications of trigonometric ratios of complementary angles which we have derived in the recent session connected with real life applications. Now one of the applications is where when I have the trigonometric ratios in the product, generally we try to use the formulae sine 90 minus theta, cos 90 minus theta or tan 90 minus theta. These kind of problems are simplified more using the topic of trigonometric ratios of complementary angles. So let's see one of the example problem where I would like to simplify tan 48 degrees times tan 16 degrees times tan 42 degrees times tan 74 degrees. So in order to simplify this value, let's try to rearrange in the form where I don't disturb the first two products, tan 48 times tan 16, but here tan 42 I tend to write as tan 90 minus 48 because 90 minus 48 is 42. So this 42 is written as 90 minus 48. Similarly, I take the last trigonometric ratio and write this 74 as 90 minus 16, which gives me 74 degrees. So exactly my 74 degrees being 90 minus 16 is substituted in place of this, and this is transferred as 90 minus 48. So undisturbing the whole expression, let's see what exactly would be the outcome. So coming to the next, this is tan 48 as it is, and this is tan 16 as it is. But next, tan 90 minus theta is cot theta is what we have as the formula, which is recently defined to be cot theta is the formula which I am going to use out here. Therefore, substituting tan 90 minus 48 would be cot 48 using this formula. Therefore, I get this as cot 48 times. Similarly, tan 90 minus 16 using this formula would give me cot 16 degrees. So this is strictly because of the formula which I have here. Tan 90 minus theta is cot theta. Simplifying this further, I have this as tan 48 times tan 16 times. Now we know that you have a formula which says that cot theta is reciprocal of tan, or tan is reciprocal of tan, I have cot theta is 1 by tan theta. Therefore, my cot 48 I can write as 1 by tan 48. Similarly, my cot 16 would be 1 by tan 16 using the formula. Is what I get from this formula. Now next, immediately I see that these two tan 48s get cancelled because one is in the numerator and one is in the denominator. Similarly, this and this gets cancelled, and I get finally 1, which is said to be the required answer. So this is the required answer. That is, when I simplify this product, I get the answer as 1, strictly using the trigonometric ratio of complementary angles, one of the applications in the branch of mathematics. So trigonometric identities is the topic of the session. So what are trigonometric identities? Or basically, what are the identities in mathematics? Say for example, I take a plus b whole square. We clearly identify that a plus b whole square is a square plus 2ab plus b square, and this holds true for any a and b. Universally, you take any value of a and any value of b in mathematics, it is mathematically true that a plus b whole square is equal to a square plus 2ab plus b square. This proves that it is an identity because it is universally true for any two values taken for a and b. So such expressions which are equated to be true for all values are said to be identities. So trigonometric ratios are also connected with identities. There are some basic identities for which you take any angle and substitute in the equation, you get equal. One of the identity which we are going to prove here, the trigonometric identity which we are going to prove out here. So let's see what is the first trigonometric identity which we are going to derive out of the trigonometric ratios. So initially, to come with, I'll consider a right angled triangle ABC to start with identifying the first trigonometric identity. So let's take a right angled triangle A, B, and C, and this is theta. So in this, I have my opposite side is this, my adjacent side is this, and my hypotenuse is this. Therefore, by using the Pythagoras theorem, I clearly have, by Pythagoras theorem, hypotenuse square is opposite square plus adjacent square. So here, what I do is I divide the whole equation by h square. Let's see what happens if I divide the whole equation with h square on both sides, the left hand side and the right hand side. So h square by h square would be O square plus A square by h square is what I get when I just divide both sides of the equation. Immediately I can cancel this because they are equal in the numerator and the denominator. So let's see what happens when I take this. I take this to the left, I get this as O square plus A square by h square equals 1. When I simplify this further, I can split this as O square by h square plus A square by h square equals 1. Splitting the denominator, it goes into each of the term as O square by h square. Simplifying this further, I get this as. So when I split the denominator, it goes into each of the term as O square by h square plus A square by h square equal to 1. And when I simplify this further, I get this continued as O square by h square, which I can write as O by h whole square, and A square by h square, which I can write as A by h whole square. Using the laws of indices, I get this equal to 1. A power m by b power m is a by b whole power m, the law of index, which I have applied out here. So in this case, my opposite by hypotenuse is sine theta, because we have already discussed about the trigonometric ratios where opposite by hypotenuse is sine theta, which is opposite side by hypotenuse, whole square, plus adjacent by hypotenuse is cos theta, which we have already identified in the trigonometric ratios. Therefore, cos theta is adjacent by hypotenuse. So in place of this, I get cos theta whole square equals 1. Now, usually the powers of the sine are written before the angle. The notation and the rule of writing the power for a trigonometric ratio is we don't write sine theta whole square, but we write sine square theta plus cos square theta equals 1. It comes after this, where sine square theta is assumed as sine theta times sine theta, cos square theta is assumed as cos theta times cos theta, and then this is the trigonometric identity which is identified in case of the trigonometric ratios sine and cos. So the first identity we have identified is sine square theta plus cos square theta is always equal to 1. When I square the sine, I square the cos and add them, I get 1. Of course, for the same angle, theta is the first trigonometric identity. So dividing the whole equation, let's see what happens if I divide with a square. Let's see if there's a new trigonometric identity which I can discover out of dividing the whole equation by a square. Previously, I divided with h square. Then now I attempt on dividing the whole equation by a square. And then finally, let's see in the next session of what happens when I divide the whole equation by rho square. So initially, here to start with, dividing the whole equation by a square. Then I get here rho square plus a square by a square equals h square by a square is what I get. When I split the term, each of the terms through the denominator, then this reduces to rho square by a square plus a square by a square is h square by a square is what is obtained when this is further simplified. So that this and this being same get cancelled and I get 1. That implies I get this as rho square by a square plus 1 is h square by a square. This gets reduced to 1. Now this, when rearranged through the law of index, I get this to be rho by a whole square raised to the power 2 on the whole plus 1 equals h by a whole raised to 2. Now comes the question of the trigonometric ratios. What is opposite by adjacent? We have seen that opposite by adjacent is tan theta for the right angle triangle ABC with angle theta. Opposite by adjacent is tan theta. Therefore, I get this as tan theta whole square plus 1 equals hypotenuse by adjacent is secant theta, because adjacent by hypotenuse is cosine theta. So reciprocal of cosine is h by a is identified to be secant theta using its respective formula as discussed in the previous sessions. That implies when I rearrange, this is reduced as 1 plus tan square theta equals secant square theta is one of the identity which is identified in trigonometric ratios. The second identity identified here is that 1 plus tan square theta is always equal to the secant square theta for any angle theta. The second identity of trigonometric ratios. Now dividing the whole equation by finally with rho square, let's see what is the trigonometric identity we derive out of dividing the whole equation by rho square. So in this case, rho square plus a square by rho square equals h square by rho square when both the sides of the equations are divided with rho square. So proceeding similarly by splitting each of the terms I get this as h square by o square. Thus, these two being equal gets cancelled and I get 1 plus a square by o square equals h square by o square. Now proceeding similarly with this, I get this to be 1 plus a by a square by o square, I write as a by o whole square, and then the right hand side I get h by o whole square, and then that implies 1 plus a by o, opposite by adjacent is tan theta, so adjacent by opposite is clearly cot theta in its respective trigonometric ratios. Therefore, a by o is substituted for cot theta, and h by o is cosecant theta, because the reverse of sine, this is reverse of sine, which is cosecant. Therefore, hypotenuse by opposite is cosecant theta whole square is what we get. So this, on rearranging, I get 1 plus cot square theta is identically equal to cosecant square theta. Is the third trigonometric identity identified connecting the trigonometric ratios for the right angled triangle ABC. Is how we understand each of the trigonometric identities, the most important of them being the three identities which we have derived.